My name is Moshik Hershcovitch, and I'm going to present our work on prefix siphoning, an information disclosure attack on LSM trees using range filters. This work was done with Adi Kaufman and Morrison from Tel Aviv University, so let's get started. I will show how we can reveal keys from a key-value store by leveraging its internal mechanism. Many data store systems, such as object storage, databases, and storage systems, use key-value stores as their storage engine. In the figure, you can see a user sending a request to the system. The key-value store is the storage engine of the system, and the system returns a response to the user. A key-value store provides a dictionary-like abstraction with the following operations. Put associates value with the key. Get, also called point query, returns the value that is associated with the key. And range query, which retrieves the values of keys in a specific range. We usually think of key-value stores as important for performance, but many systems also depend on them for security. The system stores access control lists, or ACLs, as value metadata in the key-value store. The system decides whether a user request is authorized by checking the ACL associated with the key. This approach blocks user from making unauthorized query, but if the key-value store is vulnerable to a timing attack, a malicious user can exploit differences in query response time to glean information about stored data in the system. In the figure, the attacker can distinguish between a get that takes 5 microseconds, like sports car, versus 50 microseconds, like a semi-trailer. If the key-value store is vulnerable to a timing attack, the entire system can also become vulnerable because the system relies on the key-value response time. To date, timing attacks on key-value stores focus on revealing information about the values by leveraging external mechanisms such as memory deduplication and memory compression. However, in this paper, we point out that revealing keys can also be a security threat. Keys may be explicitly secret, or keys may be implicitly considered secret when users expect keys to be hard to guess. Keys can be explicitly secret when they contain secret data of the larger system. For example, database systems like CockroachDB and MyRocks use key-value storage engine to store data. In this system, the row's data is stored as the value, while the key contains subset of cells from the original row, for example, the primary key. So revealing a key of the key-value store reveals information stored in the database. In some systems, keys are not formally secret, but users may expect them to be hard to guess. Key-value stores often map object IDs to their location in the object storage system. So revealing valid keys is equal to revealing object IDs. While objects typically have ACLs, users often misconfigure them. Therefore, finding object IDs can be exploited for further attacks. This is a real concern since mixed configuration have already exposed personal information. In our work, as the keys can be security threat, we show a timing attack called prefix siphoning that finds prefixes of keys and in some cases can reveal full keys. Prefix siphoning exploits range filters, which are an internal key-value mechanism. One of the main novelties is that we created an attack template for all range filters that have specific properties. An important property is that these range filters store information about key prefixes. In addition, we demonstrate our attack against RocksDB with 2 different types of range filters. Our threat model is an unprivileged attacker that can send requests to the system and can only measure the response time. The attacker cannot compromise the system in any other way. We assume that the attacker can craft requests that make the system perform specific point queries on the key-value store. For simplicity, we refer to this as querying the key-value store. We focused on system using a right-optimized key-value store based on log structure merge trees or LSM trees. An LSM tree consists of 2 main components, a memory buffer called memtable and a set of files stored in different layers in the secondary storage, here in blue. During a GET query, if the key is not found in the mem table, the search starts from level 0 and moves up. LSM-Tree improves query performance by using in-memory filters to reduce storage accesses. So what exactly is a filter, and how does it improve query performance? A filter is a data structure for approximately maintaining a set of keys. When we query a filter for a key, if the key exists in the set, the filter must return a hit, positive response. If the key does not exist in the set, the filter will usually return a miss, a true negative response. But with some probability, the filter is allowed to return a false positive response. The false positive response, FPR, is the probability that a key is a false positive. The LSM-Tree maintains a filter for each file. Before a query reads a file from the secondary storage, it queries the filter. If the filter returns a miss, the key is guaranteed not to be in the file, so it doesn't need to access the secondary storage. Standard filters support only point queries, so they are not helpful for range queries. This motivated development of range filters. Range filters add support for range queries, like is there a key in the range X to Y? We observed that in some range filters, the range query support affect their point query implementation, making them vulnerable to a timing attack. Okay, now let's delve into our attack. Prefix siphoning attack is a general template for timing attack on systems that use LSM-Tree with vulnerable range filters. It can reveal key prefixes or fault keys from the system. The main property that our attack exploits is that vulnerable range filters store key prefix information, which the attacker can reveal by measuring point query response time. What makes a filter vulnerable to a timing attacks? The basic properties are the attacker needs to distinguish between a filter hit and a filter miss by measuring time, and the false positive rate should be reasonable. These are enough for a simple brute force attack. Just query for random keys and measure the query response time. The response time will be slow for an existent key because the filter will return a hit and the LSM-Tree will access the storage. And the response time will be fast if the filter will reject the key. However, this attack is infeasible for typical key space. The probability of guessing an existing key is too low, so the attack needs an infeasible number of queries. Now let's see the properties for range filters that make the attack feasible. The main one is that the false positive key shares a prefix with the key in the dataset with high probability. In addition, finding a false positive key takes a constant number of queries. We call this function findFPK, find false positive key. Last property, when a given false positive key, the number of queries to reveal the shared prefix is low, linear in the key length. We call this function ID prefix identify prefix. The find FPK and the ID prefix algorithms are specific to the target range filter. Let's go over the attack template of the prefix siphoning attack. Before initiating the attack, we need to distinguish between a filter hit and a filter miss. We called it step 0. To do this, we run point queries of random keys and build a distribution of response time. The distribution will have 2 peaks, one for the average fast response and one for the average of slow response. We can use a threshold that can distinguish between a fast response indicating a filter miss and a slow response indicating a filter hit. The main attack consists of 2 steps and the optional 3rd step. In step 1, we find false positive key using find FPK. During step 2, we identify prefixes using ID prefix on the false positive keys found in step 1. After this step, we have revealed all the prefixes of the false positive keys. In some cases, prefix siphoning can extract the full key, not only the prefix. This happens when the attacked system response distinguishes between a key that does not exist and a key that exists, but the user is unauthorized to access. For such system, we continue to step 3. The attacker scans all possible suffixes for each prefix found in step 2, querying for the combination of prefix plus suffix until it receives permission denied, instead of not found. Step 3 can be performed concurrently without the need for time measurements. We demonstrate the prefix siphoning attack on 2 vulnerable range filters. The first one is SERF, a succinct range filter introduced in SIGMOD 2018. In addition, our paper presents an attack on the prefix bloom filter. This is the filter that RocksDB currently uses to speed up range queries. Attacking prefix bloom filter is less effective than attacking SERF, but it's still 3 orders of magnitude better than a brute force attack. I'll focus only on attacking SERF in this talk. So now let's delve into SERF. SERF is a succinct range filter based on a prune trie. In its basic variant called SERF base, SERF prunes the trie and saves the shared prefix along with 1 extra byte. For example, consider the dataset with the words useful, USENIX, and users. These words share a common prefix of 3 bytes, and SERF stored the 3-byte prefix along with 1 extra byte. During query, SERF traverses the prune trie, and if the last match is a leaf, the filter returns a hit, and if the last match is an internal node, the filter returns a miss. Now let's see SERF vulnerability. Suppose we query for the key usenet that does not exist in the dataset. SERF traverses the trie with usenet USE, and last match during the traversal is the leaf node N. SERF returns a hit even though usenet is not in the dataset because the trie is pruned. You can see that usenet shares a prefix with USENIX. The main insight is that the filter hit shares a common prefix with a key in the dataset. In this case, it is USEN. In fact, this prefix is the longest common prefix. For example, useful and users share only 3 bytes with usenet. Based on this observation, I will now explain the prefix siphoning attack on SERF base. Soon we already know how to distinguish between a filter hit and a filter miss using time measurements. In step 1, we need to find false positive keys. The idea is simple. We query for random keys until we find a positive key, which is very likely to be a false positive. This works because the FPR is reasonable. For example, if the FPR is 1%, we need about 100 guesses to find false positive. Let's assume we guessed usenet, and the filter returns a hit. Next, we wish to identify the prefix. We remove 1 byte at a time from the false positive key, usenet in our example, until we get a miss, again based on time measurements. For USENE and USEN, the filter returns a hit, since while traversing SERF, they both reach the leaf node N. However, for use, the filter returns a miss, since while traversing SERF, SERF reaches the internal node E. From this step, we extract the prefix USEN, which is the last hit. Finally, assuming the system responds differently for a key not found N, an unauthorized key, we can use brute force to scan all possible suffixes of USEN and extract the key USENIX. There are other variants of SERF that aim to reduce the false positive rate. They do it by adding different types of information to the prune trie. SERF real includes bits of the original key. SERF hash stores the hash function of the original key. We explain how to attack these variants in the paper. Now I will present a demonstration of the SERF prefix siphoning attack. I will demonstrate it against the SERF real variant. The paper contains also demonstration against the other variants. We evaluated the attack against RocksDB, which is the most popular LSM-Tree implementation. We use the publicly available SERF code integration into RocksDB. We populate RocksDB with a dataset of 50 million uniformly random 60-bit keys. We picked a uniformly random dataset as it represents the worst-case scenario for our attack. We run threads in the background to load the system during the attack. Now let's discuss the attack steps. In step 0, we ran 10 million queries. In step 1, we run also 10 million queries. In step 2, we identify the shared prefix of all the false positive keys from step 1. In step 3, we scan the suffixes of all the false positive keys that have a prefix of at least 40 bits. We perform the scanning of the remaining 24 bits in parallel. For distinguishing between a filter hit and a filter miss, we build a distribution of all the queries' response time. For a filter miss, the response time should be fast. In the figure, we can see that 97% of the queries took less than 25 microseconds, which indicates a filter miss. Now let's zoom in and take the total number of queries that took more than 25 microseconds. Out of the total number of queries, I show here in green only the false positives. We can see that 98% of the false positive took more than 50 microseconds, and also the major portion of query in this range above 50 microseconds are false positive, which is in green. This is why we can pick threshold that can distinguish between a filter hit and a filter miss. This figure evaluates the efficiency of full key extraction step 1, 2, and 3. We measure the average number of get operations per extracted key as a function of the attack progress. The average number of queries per extracted key converged to less than 10 million queries. This attack is more than 4 orders of magnitude better than brute force. How can we mitigate prefix siphoning? Unfortunately, every potential solution seems to require some trade-off. I will briefly discuss some mitigation. The system could make sure to query the key value store only for authorized key, but that requires re-architecting the system to keep ACLs outside of the key value store. The system could also rate limit user requests, but that hurts performance. The key value store could use the range filter only for range queries and keep another filter for point queries, but this wastes memory. Finally, a range filter may not be vulnerable. For example, Rosetta from Sigmund 2020. However, Rosetta does not handle variable length keys well, which limits its applicability. To conclude, we point out that revealing keys can be a security threat in some cases. We introduced prefix siphoning, a general template for revealing prefixes or full keys by a timing attack. We showed that range filters make LSM-trees vulnerable to our attack if they have certain properties. An important property is that these range filters store information about key prefixes. Our results show how the performance improvements, even in internal mechanism, can lead to security vulnerability. And we hope that this focus on vulnerable range filters will inspire research on more secure filters. Thank you.